So I will talk about the dynamics of degenerate PDE for modern epitaxial closing. So let's see. So so what is the PDE I met? So it's a very special PDE. It's h is height, the time derivative, and involve p-Laplace. And then exponentially, e to minus p-Laplace and nano-Laplace. So that is PDE, what I encountered. And let me say, first was introduced to me by my the colleague and neighbor in the UNC, Jeremy Mottola. He said he wrote a paper with Jonathan Worth on this derive this PDE. So this derivation indeed sort of for the derived the equation, which was early time were Kloger and Dobis and Majanimi in 95 derived this PDE. So what is PDE about? The PDE about this guy, suppose p equal to 1, then this p-Laplace is a curvature. So this is basically kind of the surface diffusion with exponential curvature. So that's sort of the equation, have a very special property which describe unsymmetrical in evolution of convex and concave part of surface. I guess we heard about this morning, first talk, some of experiment data, which is shows some unsymmetrical property on the surface evolution. Okay, that's sort of connect this guy. So, so I will more focus on the PD side of this question. And that's indeed a very tricky PDE, as not much structure we try to understand. That's how I'll get interested in the subject. So then also same time, so also I look into the little bit literature on some related problems in hoping find some of physical understanding on the model. And so then we, besides these two references, mainly then also we found a reference in 92 by Zangber and collaborators, and sort of studying this called unsymmetrical property for evolution. And there's sort of some exponential form will appears. So that's the one. And another probably really influenced us is the Morling's paper, 57. And when he considered about the evaporation, then it's instead of the forced equation, they studying signal equation. With deposition, evaporation, and signal equation, instead of the R2 gradient flow become H minus gradient flow. So as the equation, Morling will write down the equation. So is a curvature equation, but the exponential mass kappa. And his purpose is studying understanding thermal behavior of glovings. I'm going to say this actually the solution which Morling has is actually is important to our understanding the force of the PDE. Okay, so I will come back to a particular solution which the Morling's was derived for studying this dynamic. And then also some PD analysis by sort of Giga's group, Yoshigiga and their student use the viscous solution because signal equation, you have comparison and you can establish these solutions for this exponential curvature equation. Okay, so let me, so the derivation for the paper, although it's the simplified earlier one and still complicated. And he used a language called optimal twist, which comes from the Hirschsprung and Funaka. So there's a review article by the Funaka is actually quite relatable. So instead of go through the details from this optimal twist, what in the language, let's say, trying to understanding in the simplest possible way what it meant. So how does this come from? Okay. So let's say, let's classical, solid on solid, the bond counting for crystal closing. And so then let H be the height of the thin film. And the atoms sort of deposition and hovering along the surface and assuming atoms are dilute. And assuming atoms are the dilute gas. Okay, so then in the case without the deposition or evaporation, then it's conservative system, and then we'll see how this the exponential PD naturally going rising. Okay, and then later on we see if in the case with the deposition, evaporation, we will see how the signal then comes up like a Mullins derivation. Okay, all right, so let's see. So, regard the other atoms hovering around the substring because dilute gas, then it's basically satisfy Fock's law. And J is the flux, which giving minus gradient of the density. So now, and we know surface is the morphology is not smooth, and then locally, and locally this gas, dilute gas, of course, satisfy ground canonic assembling, and which satisfy by E to minus beta, energy minus nu, and is sort of the energy and chemical potential per atom. So now you look at this guy itself. Suppose the energy not change much. You lump into this all this energy part by the baseline, then you come up naturally exponential positive beta nu. Nu is the chemical potential. So normally what we see, the equation is in the form linearized form. So suppose in the high temperature, then normally exponential beta nu, which is 1 plus beta nu, and that's what we see usual surface diffusion equation come out. Okay, so now let's see. So let's mixing understanding the what a new chemical potential from, which reading the David's paper. Okay, so let's see. So try to understand in the simplest possible case, and without considering any elastic contribution, just counting bonds, use simplest possible called a solid on solid model, and then since make is skew periodic. And then you just, if you're assuming energy just for minus gamma, for number of bonds, then this energy have here, indeed is classical. SOS is have the bulk energy and the surface energy. And the bulk energy is a constant. And nothing contribute to the violation of dynamic. And the surface energy have very clean, simple formulation. It's sort of the mean curvature. And it's like L1 1. So that is so 1. And then we're reading the paper by Hepspong and David in '94. And so the general form, there's argument by David, and that says this general energy form shall be L1 plus L cubic plus alpha, so that's Lidington. And David argues is L2 will never appears. There's singularity in asymptotics. So that was how and this also form also was proposed by Spong. Okay. So let's say nevertheless, and this was meant to emphasize the PDE talk. So we just treating general the energy in this the Banach space LP form. And then, of course, you compute the first violation, you get the chemical potential is minus p-Laplace, the p-Laplace. Okay, so then you plug in back to the formula we had before as a fixed law, and it's naturally, you see, is exactly have the Laplace exponential Laplace minus pH. So that is how the equation in these models come from. I guess just giving a simplest way derive. I don't know how rigorous it is, but that's my view of the problem. So now, what is this equation means? So first of all, let's looking back to the violational. So if for the exponential particular form, you can recast in the mobility form. So that means you just usually this p-Laplace or curvature term, then multiply this sort of the H minus gradient flow with mobility. But this mobility is very special. And mobility involved sort of the curvature, exponential nonlinearity. And it's the way have here mix fast diffusion and slow diffusion at the same time. So it's really depend on the surface concave up or concave down. So this giving rising is exponential, go to infinity or zero. So it's really drastically change in mobility in the dynamics. So that is interesting to problem, and that's probably also make this PDE analysis for this equation interesting. So that is, well, I guess I mentioned this original paper have more physical derivations. So then in case we are also interested in the evaporation or deposition, then we also will cover this signal term by Morley in 57, in addition to force term. That's a paper with my postdoc Jian-Guo, and this is my colleague Jian-Guo Liu, and this Jeremy Masola. Okay, so let me now start to look at the PDE. So what is PDE? So the Xiaosheng was visiting, Sabelic visiting the Duke, and I just bring to this question to him. So let's say, look at this PDE, and studying the simplest case in the P=2, and see if we can understand some of behavior for this little wide PDE. So now, first of all, look at PDE, you will see what solution will be in this, what is the natural solution space, as the first question asked. And since we try to do estimate, nothing gonna work. So we just look at this, what's the worst scenario, and found a singular solution, so a stationary singular solution, and given by this very simple sort of this polynomial with cusp. So with the angle. And then, and later on, we found out that this particular solution indeed exactly the solution of Morley in 57 for Glovin's solution. So that is exactly so. This solution tells us, and writing sort of the singular solution in the sense, Laplacian for this h is the involved delta function. So now you have this Radon measure, involved measure, then you need to put a test on top of exponentially term. So you have a nonlinear function of measure and how to make sense of it. So that's sort of the first question we had to deal with. So that's the first question deal with. So naturally, so what is this? So e to the minus function, e to minus infinity is 0. So you basically trust this term in some way we can slow it away. And how we can rigorously justify, we can make sense for the problem. Okay, so as how to make sense, that's the main probably main task we use. What the solution means, in which sense? Okay, so now naturally, you're doing the sort of bigger decomposition for this Radon measure, have the regular part and a singular part. And a singular part have the measure 0. Okay, so now, in order to do this, and you make sure this delta mass only positive, they never have a negative term. Indeed, it's quite easy to see. For this particular, we obviously use the groove down. Let me write down the groove. Okay, just groove down solution. It's delta mass is always grooving down. Okay, thank you. Yeah. Okay, so this Morley solution, there's just solution itself. We have this guy. You have this guy, and of course, his motivation for the other purpose I'm going to not digest in here. All right. So now, so how to guarantee this delta mass is this one obviously going down? That's indeed very easy to explain. So indeed, look at the equation itself, and there's sort of another free energy. And this free energy is like a beam type free energy, exponential minus Laplace h, this free energy. And then sort of we have certainly very simple Gaussian flow. And that means these are bounded. Now if this is bounded, you're doing tail expansion, and you just only have p times itself, you should take a negative part of this Radon measure, and then IP norm is bounded, and tell you that no concentration for this Radon measure for the negative part. So naturally, I have the good property, what we expect. So by this, then we propose a new notion of a solution. So what we met solution means that the Radon measure, Laplace h is the Radon measure, which makes this equation satisfied almost everywhere. Okay, so we just simply remove this singular part, and then of course why and how to justify the sense. So that's what we see. So that basically we say I want to make sure this is a solution in a sense. Okay, so we have a number of ways to explain. And first of all, with the traditional PDE, and that means construct solution through some regularization. But this regularization we found is indeed quite special. So we're doing time discretization, and it's still for the nonlinear system. And then what we have did here is add sort of some regularization. Turn tau is a small parameter, go to 0, the time stepping. And then this use little special is instead of use first order singular solution, we use signal regularization. It's really weakly with one, and that should be enough guarantee this system, elliptic system, that solution. And we have all the apparent estimate we need. And indeed, we can justify the limit as tau to 0 is indeed convergent to this PDE. So we prove global exists solution for this equation. Okay, so now, after found this solution, then this new notion for solution, we certainly ask how general it is. So what is it about? I mean, it's just a miracle and for a particular solution, or what is the general class of solution which sensible to the problem? And so then, so we work use sort of tools, use minimum movement in gradient flow. Then we see indeed, I'll show you next, said indeed a sort of Lagrange transformation for the nonlinear functional. And it turns out I can explain indeed the idea what we found from the solution itself. Indeed, I was very lucky have a great referee tell us a reference, say, look, your notion for solution indeed not new. Indeed is although for this problem, but really is a classical paper by Goffman and Celine, and later on by Taman, and there's some sort of nonlinear functional for measure. And so that's sort of the unconditioned, sublinear, and convex. Then you can define the solution. And indeed, our general formulation in gradient flow, we can justify our notion for solution exactly in the sense of Celine. And then of course I will realize many work, I guess, on this kind of generalized functional for Radon measure. Okay, all right. So let me just say a little bit on how we can cast in the subdifferential gradient flow for this singular equation, and with the notion come out naturally from Celine's work. Okay, so now it's the natural working space is the R2 mean 0, and then you ask that sort of ambient space and the working space is sort of gradient U is the RP, and Laplace U is in the Radon measure, and satisfy sort of the competitive condition. And then you impose this Banach space known. And then, of course, the notion what we have here, remove singular part means you just basically you construct a convex functional, and you remove it and justify limit still satisfied. So as usual, like just a pure estimate in PDE or in the convex mass, just apply some sort of construct additional constraint by the functional. Okay, just impose on the condition. And this condition, later on, we all justify limit is satisfied, like appear. Okay, so now the technical part I cannot involve tell you because basically in the weak law semi-continuity, just use notion in calculus evaluation. So I'm gonna skip. So now back to the question. So we doing this limiting process. There's a solution. And the solution is indeed the weak solution we defined, and it is consistent with Celine's work. So let's back to look at apply Celine's work to our particular example. So look at this exponential function, and its Legendre due is given by this simple function, and the solution behind the 2. So then you define, according to Celine, for sublinear function, and it's convex, then you can define this nonlinear functional for Radon measure by this sort of linearized in the weak formulation. So then we can prove our limit itself indeed satisfy exactly notion of Celine, and then we establish gradient flow in the setting. So that is how this setup. Okay, all right. So So let me look at this solution itself. Okay, so that's the results. So you have the global strong solution, and we can say the different proofs. Then, of course, you have all the violation property. I'm going to skip. So basically, main question is a singular part is removed by only take the regular part as a notion for solution, and then naturally in the maximum mountain operator setting for this problem, just by the the early work on this nonlinear functional, nonlinear semi-group analysis is all work out easily. So let's. Okay, I have some time. Okay, so the equation is interesting, and we know this kind of degenerate equation itself. And then the next question, when you have global sort of smooth solution, when the solution becomes bad, and it was a singularity nature, because anything traditional way to understanding singularity does not work. Anything involved exponential function or local function, this formal extension try to cause asymptotic behavior doesn't work. Okay, so nevertheless, so that's the work with Bob Strong from Penn. So then at the same time, independently, we have another work at the same time is we'll work on the condition called weak small data solution. So in the language of Wiener algebra, basically means Alban space for this natural space for that. So suppose Wiener algebra for Laplacian initial data less than 1/10, then is a global solution, and as wish you like. Basically, the decay property, anything, whatever analytically, the radius analytically increase like T2 1 support, is everything sharp in terms of sort of PDE, same as the sort of the biharmonic behaviors. So the PDE side is completely characterized study. Okay, so let me, I still have some time, talk the second part of the story. So that is the more challenging part, the P equal to 1. So that's the Liu problem for motion by mean curvature, for the surface diffusion with curvature, and how to understanding the behavior for this one. So let me mixing with exact solution, numerics, and partial analytical results, just usual part math we do, because that's the hard part. Okay, so let's see. So back to this classical work by now it's Giga, Yoshi Giga, and Minho Giga. And they studying this very simple H minus of gradient flow, total violation flow for this the surface diffusion equation, one-dimensional. And then the solution is a discontinuity, just like a shock. So basically, says this part, nothing touch, then the boundary move with sort of like the long-going condition, and the surface is going to come down. So then Giga will be justified the solution for this one. And they follow the idea of the, indeed we here talk morning or yesterday is I sort of use Kahn Hoffman vector. He actually, Yoshiki also told me he's studying this exponential PD in this setting. Okay, for this guy, so the paper with my colleague Jian-Guo Liu, dear Makadidis, I had a lot to discuss with him, understanding the thin film question, of course, again, Jilly Masula. And for this exponential PDE and the behavior for this discontinuity facet solution almost the same. So except the dynamic of this curve is differently. So for this top of phase, we have the sort of ODE is basically construct a solution, how the interface move by the ODE, then bottom is unsymmetrical. So that's one. So that's why we found this close, when I say close formation in terms of ODE. So then we justify by numerics. So see if this behavior is real behavior, and indeed it is. So we will try to apply this sort of minimum movement algorithm, and sort of we try to compute this guy, and it's very painful. I'm going to explain how to handle this sort of minimum movement with mobility. Okay, so the behavior itself, if the linear problem, linear usual one, and then symmetrical. If for the for the exponential PDE, it's unsymmetrical if we begin initially very simple sine function. And then we justify calculations for the ODE dynamic and the PDE calculations that agree well. So we thought. So So then, what we did there, it was very painful because the equation involved exponential mobility, which at some point have the very stiff. So because at one point, exponential large and exponential slows. Range of this, the diffusion coefficients like tremendous. So it's very stiff. So now next question, what we say is how to overcome stiffness. I guess I need to speed up a little bit. So then we sort of back to the PDE proof with the shoe, and indeed the exist proof always provide good numerical algorithm. Indeed, so indeed the PDE proof itself indeed provided instead of minimum moment, and it works like very nice for P. But if P equal to 1, then it's sort of slightly oscillations still there. We try to overcome. So now we come back. This beautiful work by Shangban Park, and it's for minimum movement, and this is the difficult problem itself. This Laplacian H minus of gradient flow because involved exponential mobility, which can be exponential large or exponential small depending on the curvature. So they are singular. So then this usually minimum movement does not work. So we now apply to this beautiful algorithm and the cast in the minimax problem. Basically, the cast exponential. This the Alvin norm in terms of the super the one. Then and with some of slightly modification. Basically, instead of use R2 regularization, we have to use H1 regularization. Then works like charming. So we're quite happy that the numerics method itself with actually all this minimum movement when involved mobility, except the constant loop by JKO, all other mobility is very hard to handle analysis or PDE or numerics. So that works nicely. So let me back to the last point. So can we see something analytical results on the P equal to 1? So that's the work by my first daughter, Jian-Guo, and she will be carried on, go on with my early work with her and the Jian-Guo Liu, former collaborative with Giovanni. So that's so let's say if P equal to 1, can we now sort of minimum movement either works beautifully or no way to do it, right? So as you have to say structure exactly right. So here are two modifications. First of all, instead of L1, you take L1 and log L1. It's very natural in kinetic theorem. Somehow it's not used in calculus evaluation. And it's put in there. Let's see the place more magic. Okay, then additionally, we learned from Bob Cohn, I said there's the natural mobility called attached detachment mobility from this step dynamic. It's naturally come. If we give in this the attachment, then you plug in here, and then for this with this free energy, it's almost L1 with local collection, and with this ADL mobility, then the system indeed comes down naturally in the minimum movement setting, then global solution exists. So that's her work. Proved one, and then sort of there's a results global solution, like a relative solution over there as way. And this here sort of this particular free energy was chosen for subdifferential theory. With this, I thank you very much for your attention.
Questions? So the solid-on-solid model is rather simple.
It's very simple. I just try to understand.
So,
yes.
You have in nature you have very rarely the case of
a
simple
particular. Yes, I agree. Yes, yes.
Surface. So, do you see some relevance to epitaxial systems that are already in the cubic system much more complicated when you have FCC or BCC? Or,
yeah. Well, I do. Let's see. I guess. So I guess let me try to understand your question. So for this particular free energy, I guess what I learned is mostly from David. Maybe David can okay, I put the answer for. So I guess and also help Spoon. So this is how I, and of course counting for SOS just for the p equal to 1, and that's a very simple one, and that's very easy to understand. Then any p, indeed I see all the paper film logic. Okay, you just make up the sort of bound counting a particular one. This only p equal to 1, which to me is easy to understand. But any other things I can understand line by line, but I cannot get the physical intuition on that. Yeah. Okay, maybe.
Other questions?
Just a basic question. Is there are any result with some energy contribution coupling this evolution equation with this exponential term with an elastic problem?
Oh, you mean additional elastic problem? Yeah, that's a very good question. I hear all talk. Has very nice. I would suspect this should be very natural because we work a little bit on the dislocation with the coupling with the vectorial elastic equation. But this one we have not looked at. But the only thing is but you have very nice sort of the discontinuity, which I don't know because we do not have. We will see here the angle, so it's a little bit different on cusp. So I do not know the nature, but it's worthwhile. And also you have of course a static case, right? Yeah.
Thank you.
So all the results you presented today, they were for the conserved system without deposition,
that's right. Yes.
Right?
Yeah.
So when you put in the or you look at deposition problems, do you use the same surface flux or add a non-equilibrium type of flux?
So let me two answer. First of all, we do have derivation for the signal term with evaporation, and we did derive the equation, signal term. So secondly, and there's no any difficulty in PDE additional term, signal term, so that's what we ignored. But of course, computationally media work, and usually if we do not see the difficulty in the PDE analysis, I guess we pretend we will not see it. So, so I'm sorry, yeah, but I trust this everything works, yeah.
Just sort of a follow-up to the question about elasticity.
Yeah.
You know, even when there's no applied stresses in the problem,
yes,
there are always stresses in the problem.
Yes.
That is to say that the surface tension that exists always will induce stresses. And so one just has to be very careful about the complete continuum of models unless you build in that piece to it. And it's important on a scale which is comparable to whatever the size of the feature that you're looking at is. So if you have a faceted structure, the elasticity can be important on scales which are a few times like the facet size. So it's just a warning that there is no case where
I definitely agree. Indeed, so indeed we derive this exponential PD also with step dynamic. And then also elastic contribution. We indeed also work out the mean field limit for the infinity elastics. So, but this turns out is also can explain without use the mesoscale step dynamics. So yeah, I know elastics is definitely defect and line, but it's extremely important. And there's a lot of model. Yeah. Thanks for David.